Hello, welcome to the lessons for this week. So Monday's lesson follows on really nicely from last week. We're going to be talking about cracking, and it's a process that includes both alkenes and alkanes. So you'll start to see today a little bit of a link between the two different types of hydrocarbons that we learned about last week. So what I want you to do first of all, so it's a bit of retrieval and to see how much you've understood and retained about fractional distillation. So you've got 6 questions down the side, all based on your knowledge of fractional distillation and more about really the fractions that come off the side of it. So use that diagram to answer those questions. Pause the video now and then we'll go through the answers. Okay, lovely. So the fraction with the smallest molecular mass. So the smallest mass would be the smallest molecule, which from that would be refinery gas, the one at the top. So the fraction with the largest molecular mass, again using the diagram, would be the residue. The fraction that's used in cars, well, there's a picture and it says it's used in cars, so petrol. The highest boiling point, now we should know, one, you've got it written down the side, but also you should know that the highest boiling point are the longest chains, so they would be the higher massed ones. Again, you are looking at the residue and it says there on the diagram 340 degrees C. Sometimes even at that point it doesn't vaporise, remember it's tapped off as a liquid or a very thick viscous liquid and used in roads. The fraction which do you think an oil company can make the most money from? So likely it would be petrol, closely followed by diesel. So why do you think that is? Because there are many, many, many cars in the world. So we know that the petrol and the diesel is a lot of what we want from crude oil. So we're going to learn how we come about that today. So we're going to look at cracking. We're going to name the conditions for cracking and describe how it works and then apply it all to answer some questions. The main thing you get from today is how we can write a diagram, an equation of cracking and understand why it's so important that we do cracking. Okay, so we talked a little bit about cars already. So thinking about it, roughly how many cars are there in the world? Now there's roughly 7 billion people in the world. Some families have got 2 cars. Obviously, you've got children in there as well. So roughly, we've got about 1 billion cars on the road. And obviously, we don't take into account there. We've got lorries and other vehicles for distribution purposes. So there's a lot of vehicles on the road that require fuel. Now, if we look out of this, we've got all these different things that we learned about when we did fractional distillation, the different useful products that we can get from crude oil, the main ones. So LPG, which is your gases used in your bottled gas, such as for your camping stoves, patio heaters, barbecues, things like that. Petrol and diesel, obviously used in cars and vans and lorries and things. Paraffin, which is used in lamps. Heating oil and fuel oil are used in houses, and bitumen, which is used in the roads. So we can see there that the petrol and the diesel are the ones that oil companies are going to make the most money from, just purely because there is such a high demand for it. However, through fractional distillation, we don't get enough petrol and diesel. And we get more of these bottom 4, the paraffin to the bitumen, we get more than we need. Because we do need it, but nowhere near as much as we get. So we kind of got a bit of a problem with supply and demand for the petrol and the diesel, hence why the fuel prices change so rapidly. So what we can do is use a process called cracking. And here you can see an example of what cracking does. So you've got a long chain hydrocarbon, and after cracking, you've got an alkane, which looks slightly shorter, and you've got ethene, but you've got an alkene. So I want you to think now what you think cracking actually is, because it's another one of those definitions that you will need for your GCSE exams. So take a minute now, think about using that diagram, what cracking actually is, and then we'll write the definition. So cracking converts large hydrocarbons into smaller ones that are more useful. definitely make a note of that definition. And like I said, it is very important that you know what cracking is, what your products are, and as well what the conditions are that you need. I'm going to look at that in a minute. Okay, so an example then. We said already when we did the lesson about alkanes and when we did the lesson about fractional distillation that you can't do a lot with the long chain alkanes. They don't ignite very easily, so they don't set on fire, they don't burn very easily at all. So they're pretty useless. So if we can make them more useful and get more products that we need, like the shorter chain alkanes, we're not going to waste the stuff that we've got too much of. So we use cracking and basically it breaks it apart. And you end up with a combination of alkenes and alkanes. Now, alkenes are useful because they're reactive. We talked about that when we did the alkene lesson, and we'll look a little bit more about that in a little while. Alkanes, the shorter ones, are much more useful because they ignite more easily, they're more volatile, we can use them for burning more. So that is what we actually want. So we've gone from something that's really useless to us to two different products that are very, very useful. And the conditions you need, and this is another question that you get asked on a regular basis, what conditions do you need for cracking? You need high pressure, you need high temperature, and you need a catalyst. Now, the catalyst will be different in many of the cases for cracking. So you would have to be able to identify from the diagram what the catalyst is, but I will show you how to do that when we get to the pages with the diagram on. So high pressure, high temperature, and a catalyst are the conditions. I would advise you do make a note of that with the definition. Okay, so here we've got two different compounds. We've got our alkenes, which we go on and use to make plastics, and there'll be a whole other lesson when we talk about how alkenes make plastics. And then, as we know, our alkanes are used for fuel. So this is how we do it. Now, if we were doing it in the lab, this would be a demonstration. You're not allowed to do this by yourself because it can be quite dangerous. So I'm going to talk you through what happens, and then you're going to label the diagram. And if you want to watch a video of what happens when we would have done this in the lab, there's a link to it on class charts. So this is your diagram, this is your setup, and it looks exactly like this in the lab when we do it. Now you've got your boiling tube with all your reactants in. Now you've got the arrow, hopefully you can see on the left hand side of the screen, that represents heat. So we need a Bunsen burner. We've said we need high temperature, so that's where that comes from. Now directly above the arrow, which shows the heat, that is our catalyst. Now in a lot of occasions it's a ceramic or a porcelain catalyst, so a broken up piece of say evaporating basin, something like that, acting as the catalyst. Now to the left of that, the end of the boiling tube, you've got mineral wool that is soaked in your hydrocarbon. So rather than just putting the hydrocarbon in there as a very thick liquid, anyway, you soak mineral wool in there, it makes it safer. Then you've got the bung and a delivery tube. Now the bung is what helps build up the pressure because any products can't just escape, they would just be forced down the delivery tube. So that helps provide the high pressure. So when it does start to break down the hydrocarbon, the product gases go down the delivery tube, and we use a test tube filled with water to bubble the gas through. The water will get pushed out and you can collect the product gas in the test tube. So hopefully you'll notice, if you look back at the boiling tube on the left hand side, that you don't heat the crude oil itself. You don't heat your hydrocarbon, you heat the porcelain, you heat the catalyst. And that's very important, but it makes the reaction more safe and it makes the reaction go quickly. Now, the reason you guys don't do this in the lab and it's always a demonstration is because you've got to be very, very, very careful about how you stop this reaction. Because you've got the delivery tube going into some water, if you don't take that out first and you take the Bunsen burner away, the pressure becomes greater and the water gets sucked from the engine delivery tube into the boiling hot boiling tube and then causes it to smash and it can spread everywhere. So that's why you don't do this in the lab, because it can be quite dangerous. So it's under teacher instruction only. So what I want you to do now is I want you to make a note of this diagram, copy it down and label each of the boxes with what it says in A to F underneath, and then we'll go through the answers. Okay, lovely. So hopefully you can see that the porcelain chips, the catalyst, that was the top one. Mineral wool soaked in liquid paraffin. So your liquid paraffin is your hydrocarbon. It could have been any long-chained hydrocarbon. It was just liquid paraffin this time. Your Bunsen burner, so that's our heat in the middle. When we draw scientific diagrams, we don't draw the Bunsen burner. We just draw the arrow and write the word heat underneath it. Then you've got your boiling tube. You've got your Bunsen burner valves that you could put on if you wanted. You don't have to. And you've got your product gas being collected at the end. So now we can label our diagram and name the conditions. We're going to look, and I've already explained how it works, but look at it in a little bit more detail. So I'm going to put these two video links on class charts, and I want you to watch them and then move on through the slides. So when you have got your product gas at the end, you will have seen from before that we get a combination of alkenes and alkanes. Now it's really, really important that you understand how we can tell the difference between an alkene and an alkane, because they could all be colourless gases. So we need to be able to test what we've got to see how useful it is. Now, bromine water is what will help us to do that. Now, bromine's normally a gas. You can bubble the gas through water and get bromine water. And as you can see from the picture, it's an orange liquid. Now, that is really, really important. Now, bromine water is toxic and corrosive. You can see from the labels. It is really stinky. You don't want to breathe it in at all. So again, you have to be extremely cautious with this. Now, as you can see from the diagrams, if you add bromine water to an alkane, even if it is a gas, so you could have that test tube filled with gas and a stopper in the top, you put a few drops of bromine water, put the stopper back on and give it a shake. Nothing will happen to the bromine water. The bromine water stays orange. However, when you add bromine water to an alkene, put the stopper in, give it a shake, it's the bromine water decolorizes. So you can see I've underlined the alkene will decolorize bromine water. It's really important that you understand that. So it's a 2-mark question in an exam, and it's asked all the time how you can tell the difference of the products of cracking. And you add bromine water, that's the test. The result is the alkane, the bromine water remains orange. With an alkene, the bromine water goes from orange to colourless. Now that word is really crucial. Don't say clear, you'll get the answer wrong. The bromine water is the thing that changes colour and it goes from orange to colourless. I would make note of that now because you are going to need that many, 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 many times. Okay, so what I want you to do now is I want you to pause the video and answer these questions based on what I've just talked about and what you've just learnt so far, and then we'll go through them. So, okay, so the first one then, what is the purpose of cracking? It is to break down large hydrocarbons into smaller, more useful ones. The conditions needed, hopefully you'll know there are 3 of these. So you need high temperature, high pressure and a catalyst. You don't need to say which catalyst it is at this point. It might be labelled on your diagram as it was on ours, and you might need to identify that in a question. So the products of cracking are shorter chain alkanes and alkenes. So we've gone from large ones to small ones with alkenes in there as well, which is very useful to us. So what are the products of cracking used for? So the alkanes are used for fuels and the alkenes are used for plastics. Hopefully you got both of those down there. And how can we tell the difference between the products of cracking? So make sure you've got the test and the two different results. So you add a bromine water, that is your test, make sure you've got that. Alkanes, the bromine water stays orange, and the alkenes, the bromine water turns orange, the colourless, making sure that you know it's the bromine water that turns colour, not the alkene. If you've got and made any mistakes, make sure you correct your answers. These are really crucial things to take from cracking. So finally now we're just going to put all that together and apply it to some exam questions. So you should have seen on class charts, it's a very short sheet of questions. So I want you now to pause the video, answer these exam questions. You'll see a very familiar diagram. You'll see some alkenes below. So answer the questions and we will go through them once you're done. Okay, so lastly then, let's go through the answers. So it's exactly the same as what you've got. So they've ethene can be made when heptane vapour is passed over a hot catalyst. So heptane is the alkane. We're trying to make ethene. So draw a ring around the correct answer to complete the sentence. The process used to make ethene is called cracking. Why does pentane collect in the test tube surrounded by the cold water? Because it's condensed from a gas to a liquid. That's what the cold water is there for. It must have a different boiling point than ethene. That's why one stays as a gas and one turns into a liquid. Complete the sentences using the words on the labels. The name of the alkane that decomposes was heptane. The name of the catalyst is broken pot, which you could see from the diagram. So then you get the displayed structural formula of ethene. Remember, displayed means it shows all the bonds. So ethene is added to bromine water. What colour change will be seen when ethene is added to bromine water? So you don't need to describe the test this time. You've just got to describe the colour change, and you must say that it turns from orange for 1 mark to colourless, and that would get you the 2nd mark. If you've just said it goes colourless, you'll only get 1 mark. You've got to say what it started out as. Anytime you're describing a result, you've got to say what it went from and to. And when you move on to the unit where we're identifying ions, describing colour changes will be really, really crucial. So hopefully you found that useful. I'm hoping that you've done really well. If you've got any questions, drop me an email. You know my email address. And the next lesson we'll be looking at alkenes in more detail and looking at how they are useful to us. Thank you.